Thank you very much. Actually, my official institution right now is the Institute, where I spend a year. And I think it's the first time in life that I'm attending a conference which takes place 20 meters away from my office, which is over there. And it's very convenient. So thank you very much for the invitation. I'm going to talk about something which is almost the same talk as the previous one. Instead, I will add a quality which is to be unstable. So it is sort of the unstable analog. Unstable is an unfortunate word in English, which suggests it is something like chaotic or behave badly, and which means only, in fact, not yet stabilized. So I will not work with spectra. I will work with spaces. Okay, there will not be any P1 spectra or anything like that, just spaces and smooth varieties. But there will be some analogy, as you will see. So we fix a base field. Okay. I will basically work with smooth finite type K schemes. Let me give some elementary definitions, well known, but still. So for any integer, the standard algebraic n simplex, delta n of k, is the spectrum of the polynomial ring in n plus 1 variable, t0, tn, divided by the relation sum of the ti equal 1. Okay? So it is an affine space of dimension, it is a dimension n, but written this way, it is clear that you get a cosimplicial object in the category of smooth schemes. Okay? As such, so I will not define what is a cosimplicial object, but if you take any x smooth scheme, you can evaluate x, take the pre-sheaf, x define a functor from the opposite category to the category of sets, and you can evaluate this on this cosimplicial object. So I denote it by S point. The singular simplicial set of x, the algebraic setting, is just as a simplicial set, a morphism, in the category of smooth variety from this cosimplicial object to x. Okay? So I'm going to spend the talk, part of the talk, to see whether this, so this is what I call the naive simplicial, singular simplicial set assigned to x has any meaning or not. Is it too naive or is it anyway interesting? So of course this is part of something a little bit more general. It is a section over the base field of a simplicial sheaf. Okay, denote it this way, where so over the base field, where this is a functor from the opposite category of smooth schemes to the category of simplicial sets, which take any smooth variety to on of delta point cross u to x. It extends, of course. I just evaluated this on k. And this is a sheaf, because x is a sheaf in Zariski topology, for instance, or Nisnevich. I will use this sometime. So sometimes this guy will come into the game, but the most of the talk, the main theorem will be stated in terms of this guy. So, is this too naive? So sometime, yes, I will give very elementary example, and sometime, as you will see, it's not that naive. It contains a lot of information related to the previous talks, for instance. The problem of this simplicial set assigned to X, it is either totally trivial to compute, either it is absolutely uncomputable. You cannot start with. So if you remember, I hope most of the people here went to a class in algebraic topology once, and when you learn the definition of singular homology, you learn the definition of the singular simplicial set of singular simplices in X of the same type, and something completely huge. You cannot compute anything with that, so you have to prove theorems. The small U-chains theorem to prove Mayer-Vittori sequence and so on. Here it's basically not possible. You can try, but if X is covered by two open subsets, you can basically say nothing. Okay? Either it is completely trivial or you say nothing. So let's see the answer. Let me give some very, I told you, it is either completely trivial or first trivial example, if X has dimension 0. So it is a finite extension, separable, finite extension of K. So either it is equal to K, and this is constant equal to the point, or it is empty. So the answer is this. A simplicial set is either constant equal to the point if it is of degree 1, or it is empty. So not much interesting. Let's take to the next dimension. First, this one. It's already a little bit subtle. S point, so you have to prove it. It's not trivial. Yeah, it is the identity, but it is contractible. Using the homotopy as a simplicial set, it is really contractible using the homotopy algebraic, which is a product. If t equals 0, it is the identity of A1. If t is it is 1. If t is 0, it is just a constant map to the point and collapse everything. So already there is no much to say, but it's a little bit more interesting than the first case. If you take GM, so you move 1 point. GM is A1 rigid. You cannot map A1 to GM in any way, as a constant. So again, the simplicial set is constant. No simplicial structure. Okay. So if you take any A1 rigid, or more generally, smooth scheme, so which cannot see any A1, like a curve of genus greater or equal to 1, Abelian variety, an open subset in there, product, and so on. It's constant, there is nothing. Okay? So curve, genus, Abelian variety, and so on. Then this is the constant. Okay. So nothing happens. So this is trivial to compute, but not interesting. If you introduce, could do it here. So the main aim of this talk, definition, the homology, which I call naive, of X with Z coefficient in the singular homology of this simplicial set. So just the usual. It's a simplicial set. You take the free Abelian group in each degree, and you get a differential, the alternated sum of the faces. It's a complex, and you compute the homology. This is. So it's easy to compute here, and it's not interesting. So in the first case, you get Z or 0, the homology of the empty space is 0. Here you get Z for A1, it's a point. And for GM, you get H naive is the free. So you should not forget this. This is the reason why I give this simple example to care a little bit. It is a free Abelian group on K star, the H0. okay, concentrated in degree 0. And for the rest, it is also z on x of k. Now the last example, I will spend the rest of the talk. P1, you can say anything, no, nothing. It's just too hard. Okay? So, unknown. Well, I can maybe give some information which will be justified later in the talk. Well, one may compute a little bit. It's hard, but I told you, you cannot say right now something. But one can prove that the H1, so the abelianization of the fundamental group, it happens that I can compute the fundamental group of this set, simultaneous set, is an extension of K star by the second power of the fundamental ideal in the Witt group of K. It's a natural extension. So there is another name, it is K1 Milnor-Witt. Mark Levin used this notation, so I may. So it's the usual, it is a K1, so this is a formula which we can prove. We basically cannot prove anything else except the main theorem. It is the Milnor-Witt K theory in weight 1, which is the fiber product of K1 Milnor of K, which is this one, and the first power over what they can do, which is this one. And the fiber product fits into this sequence. Okay, okay, so this is just to remember what it is, and the rest, in higher degree, is very hard. Okay. For the PNs, the same thing happens. This is the Pn for n greater or equal to 2. So it's a funny phenomenon. Well, I won't have time to explain this. The fundamental group, in the case of P1 here, of this singular, is not commutative. Although it is a very universal object, in general it's not commutative. But this is the abelianization. The pi1 here is always commutative of the simplicial. Yeah? It is always K star. So it is automatically the H1 naive, because the pi1 is abelian. Okay? And of course, the other one are completely unknown. Maybe I should, to make this talk to keep elementary, a proof that we can sometimes compute something. You can really understand it. It's the only computation you can do, in fact, complete computation. Well, not. You will have to go to some book to compute. The second one is, the last one is P infinity union of Pn's. So it's not a scheme, but you can anyway make this construction. I claim that in a very explicit way, this naive simplicial set, where K, is homotopy equivalent to the classifying space of this fundamental group. So this is like in topology. Okay? So you can compute the naive homology completely. It is the homology of the group of units. But you have to go to a book or to take a paper and then do some computation. Okay, it depends on the torsion and so on the quality. But at least you can reach this guy. So the proof is the following. You use the canonical GM torsor here, and you so it's locally free in the Zariski topology torsor. So and you let n go to infinity, and you get exactly such a torsor here. The point is, when you apply this construction to this functor here, you get a fibration. And this is the constant guy, so it is K star. So it's really a locally trivial, principal bundle over this simplicial set. So this is constant, so it's a covering. And then you prove that this is contractible by hands. It's contractible because it is a union, okay, Sn plus 1 into S point An plus 2 minus 0, and this one is explicitly homotopic to the constant map. So it's trivial. So the colimit is contractible because you can take a homotopy to any of these to 1 here. It is a 0 section here. And when you have 1 at the last coordinate, you can collapse everything to 0. So this is basically the only complete computation you can do. You can do the same thing with the infinite Grassmannian, but then you get GL infinity, so it's already complicated. So now, what can we do else? In the title, I wanted to compare with the Suslin homology. So fortunately, Mark defined very shortly the Suslin homology, so I will be able to go a little bit quicker as planned. So comparison. I will define a map, canonical map, from this naive homology groups to the Suslin homology. So everybody has his own notation for the sheaves with transfer, free and so. Mark used Z and so on. I use the other one. So if X is a smooth variety, it is a free sheaf of abelian group with transfers on X. Free Zariski topology. Sheaf of abelian groups with transfers in the sense of Voevodsky. And its section over smooth schemes is exactly the group Mark defined. Okay? It is a free abelian group on, so I will not redefine it, integral closed subscheme Z in X cross Y, which are finite and dominant over one irreducible component of Y. Okay, it is the usual things. This can be turned into a functor, and it is the free sheaf of abelian group with transfer on this X. And the Suslin homology is defined exactly the same way, but using this functor instead of the free sheaf of abelian group. If I do the same thing, so for this reason, I get a map. So, Suslin homology with an S, X, and you can put coefficients if you want, is so the homotopy groups of the following simplicial abelian groups evaluated on delta point. So, to remind, so this is a sheaf of abelian groups. If you take the sections on the co-simplicial delta point of K, you get a simplicial abelian group. And such, okay, this one, and such as homotopy groups. And the homotopy group, as it is well known, it's the Dolkan formula, this is the homology of the associated complex to this simplicial abelian group. Just make this explicit that you do not get confused. Where is the homology and the homotopy of the complex? So such a simplicial abelian group has an associated complex which computes the homotopy groups. It's very easy to compute. So in degree n, you have the differential, which is this one. If you take a space, a variety, which is not an abelian group, you cannot do that. And to compute the homotopy group is more complicated. But if it is abelian, you can compute it this way. Now, the naive homology, if you look through, is defined by the same formula, but using the just naive free sheaf of abelian group. Because you can check that this is really the free group on the section. Nothing happened. So, from this description, get a map, canonical map here. So again, in the previous example, what happens? Is this map close to be an isomorphism? So no. In all the examples where you can compute, it's basically not an isomorphism. So example, so I will drop the first example to trivial. Example 2 for A1, okay, well, it is an isomorphism because it is trivial. It's an iso. Maybe I should theta of x. Is iso, but it's really trivial. For GM, already it's not. You get the free abelian group on the units mapping to. Then you have to work. You have to open your Orange book or something like that and to see, oh, what is the motive of GM. So, well, I did not say, but Mark did. This is exactly the same formula in degree star. It is the morphism from Z shifted by star to the motive of X. It is a Suslin homology or motivic homology, if you want. Okay? So the motive of GM is Z plus GM as a sheaf, which is denoted by Z11, but in fact concentrated in degree 0. So what we get is, but still, so it's not an isomorphism, but something happened. You get this, and it is surjective. Okay? And there is nothing else in higher dimension. But for instance, 3, for X in abelian variety, you get, so the free group on the group of points, mapping to, so the same phenomena happens, except that you cannot, I mean, the motive is complicated in high degree. I will only concentrate on degree 0 for the moment. You get Z plus, you can check using, in fact, this formula, what is the H0 Suslin here. For a smooth projective variety, in fact, it is true. It is the CH0. People say CH0. It's a group of points, the free of close points, the free modulo, the rational equivalence. So there is no way in general. It's something not so interesting. And here the homology is in a higher dimension complicated, and here there is nothing else. So it seems completely crazy. So what shows this example is that if you tend to be a rational variety, it's closer to the Suslin homology. Okay? Here it's completely different. So it's a natural phenomenon in this world. So now let me state the main theorem, which I could also mention. Yeah, I forgot P1. So P1, the H0 naive is 0. It's trivial, I mean it's Z. The same is true for the Suslin homology. And it's not like GM, because the motive of P1 is Z plus one more shift of this twisted, which is 0 in degree 0. And then something happened in degree 1. H1 naive. So H1 naive is there on the blackboard. It's minor K theory. Weight 1 of K mapping to the H1 here. You can check. There is only K star. And this is surjective. The kernel is I2. So it's better. It's connected, or what the people say CH0 universal CH0 trivial. I think I heard this. But in fact, this phenomena is not directly related to that. It's related to a stronger property that this is A1 chain connected, which is stronger, that you can really join any rational point by lines of A1. So this is surjective, and the kernel, we have an idea on what is the kernel. So there is an explanation of that. So I will not say that this is an isomorphism, but there is one reason why this naive homology cannot be isomorphic to the Suslin homology in general. The reason is, again, topology. If you are working on a field like R, the real number, you can evaluate the situation on the complex point or on the real point. And this part here is to take care of the real point. This will map to Z on the real point. And remember that P1 over the real point is a circle, and the pi1 is Z. So in fact, in this formula here, this formula is the only possible which takes care of the two phenomena. That on the complex number, it is the Riemann sphere, and on the real point, it is a circle. Okay? So there is always an explanation. And of course, if K is algebraically closed, then this is an isomorphism. Okay? But still, these phenomena, remember that. So now let me state the main theorem. And this is basically an unstable analog of what Mark talked about. Theorem 0, but I'm not sure there will be a theorem 1 anyway. So we assume, sorry, it's algebraically closed. And L is a prime number different from the characteristic. And then we have to assume something on X. So what I'm going to say is what we saw on the examples. It cannot be true in general, for a trivial reason, that there is some relation. So you have to avoid this. And so I will not make this precise, but I guess there is such a theorem, generalization, in the case where X is an A1 chain connected variety, that you can modify this statement more generally. So I will restrict myself very much here. But there is something which says that this simplicial set is not so naive for any for instance, proper smooth variety which is A1 chain connected, for which the CH0, for instance, is a Z. And here, X will be a smooth and homogeneous variety of the form G mod H. And you have to give some property on these groups depending on the characteristic. So it's easier on characteristic 0 because there are more theorems on torso in characteristic 0. So where G is semi-simple. So why semi-simple? Because if I would say an algebraic group, I could put GM, for instance, and it's already wrong. So this is to avoid GMs, okay, semi-simple. They are in some sense connected and simply connected, algebraically connected in the algebraic group theory. And H can be more general, can be reductive. So you can allow GMs in the kernel, in the isotropic group. So connected. In fact, you can, well, it depends, but you can improve this a little bit. You can assume only irreducible. And you may suppress this, not necessarily, in characteristic 0. Because in characteristic 0, if you have a finite group, the étal H1 of the affine space is trivial. And the problem here, it's not true in finite characteristics, so I have to assume that H is connected. Okay? So in that case, then, the map in model homology from the Suslin, so the naive, to the Suslin homology is an isomorphism. Suslin In fact, the proof will not be exactly to prove this. I will use exactly the theorem that Mark mentioned at the beginning. So if you're on an arbitrary field and not of characteristic 0, not embeddable in C, you cannot take the Betti realization, but you can use the étal mod L homology, which is just a dual as a ZL vector space of the étal homology. And Mark mentioned that this is an isomorphism, okay, by Suslin-Voevodsky. So what I'm going to prove is that this map here is in fact an isomorphism. So it is a rigidity property, again, but in an unstable world where I have no homology, I have just simplicial sets. So I have to prove very much on this simplicial set to be able to put them into pieces to apply such rigidity property. So basically, I prove that this is an isomorphism here, okay? Which we can check on all the examples on the blackboard. A1 is very strong. It means that for any field extension, any to f of k, any to f points can be joined by a chain of A1s. So it's very strong. You can apply this for the generic point, for instance, and so on. It's much more than... So there is some discussion in a paper I wrote with Asok where we listed exactly the list Colliot put on the blackboard. So rational, stably rational, retract, and so retract rational is A1 chain connected. But stably rationally connected is not, for instance. Yeah, so it's something it's stronger. Okay, it's not clear, but for instance, a smooth proper scheme is A1 connected in the sense with Voevodsky exactly when it is A1 chain connected. So it's the natural notion. But you have to check it for any field extension. So, and I expect that for a smooth proper scheme, which is A1 chain connected, you can modify a little bit so it will be not so naive, because I'm not sure, maybe, but there is another candidate, which is still naive. There is no transfer, there is no motive, and so on, which compute the same thing. So it means that in the homotopy sheaf, so this is a little bit the philosophy of this fact, when you are A1 chain connected, in the higher homotopy sheaves, there are still already a kind of transfer inside and a rigidity property, but they behave very well. Okay. Well, I won't have time to explain all of this, of course. So, what may I? Some comments. What about the example? So the basic example we have on the blackboard, which fits here, is the number 4. And already gave the proof in degree 1. Yeah.
So you were saying that you're not saying that G mod H is universally A1 connected?
I do, yes. Yeah, because simply connected, semi-simple and simply connected is A1 chain connected.
Yes, but G mod H is a different matter.
Yeah, but in that case, I'm only considering, I am only considering, so morphism from delta n, and in this case, an over an algebraically closed field, and any H torsor is trivial. So the simplicial set, no, I'm not saying that, I'm saying the simplicial set, my naive is connected. No, I didn't say that. No, it's only true here. It's only true here. No, but the simplicial set is connected. And basically, I showed you that there is no example except A1 or AN where it is true in degree 0 and the variety is not chain connected. But in some sense, it is the only obstruction. If you assume you are connected in this sense, in strong sense, then it seems that something happened. So remark, so in case 4, so P1, it's compatible, follows from I2 of k is trivial. for an algebraically closed field. It's on the blackboard. So it's a kind of generalization of that. But you have to understand why in the higher homology sheaves or homology groups here, there is such a phenomenon of cancellation, which it shows also, I already did, but this example shows that there is basically no reason to believe there is a theorem when K is not algebraically closed. Show that if K is general, there is no general analog. Of theorem 0. So, for instance, you could imagine, I don't know at all, here you can say, oh, if the field has no quadratic extension, okay, then I2 is 0. So it is an isomorphism in H1. So is it true in general? I don't know. You have to prove something on these groups which I don't know yet. Okay, so it's a tricky situation. So, and this is for the moment the best thing I can do. So in some sense, to summarize, I can prove this, and as you saw here, and I can basically prove it in all the cases you can compute. It is true in the first non-trivial case. Okay, you can prove it in any for any variety. Okay, I mean there is such a phenomena like this one in the first non-trivial case, which is almost always H1. I won't have time to explain this in generality. A smooth proper variety is either non-A1 connected, and if it is A1 connected, the H1 is non-trivial. So this is the only case. Basically, you can prove something more general for a general field on the H1 case. I will come back to this point later. So,
what is that for this H?
reductive. Sorry? Sorry, not necessarily. Okay, not necessarily. Okay. In fact, I think you can assume any affine algebraic group. By the structure theorem, you can reduce, but I will not. You have to know basically that all torts over the affine space are trivial, and then you can do it. Yeah. For my I thought so. I'm not sure. Okay, so connected. Okay, connected already. If not, it's wrong in finite characteristic. Yeah, fine. Okay, so maybe I can give another example right now. Okay, let me. Exactly. 3. And I will comment on that. This theorem applies for G itself. Okay, so G itself. And this is where I use the fact that it is simply connected. If not, it's not quite true. You have to care a little bit. It is true. Okay, and in fact, one of the points is that this simplicial set, which is the singular A1 simplicial sheaf over K, this one is incredibly, miraculously good. Very good. So I will not have time to explain what it means. It means it computes exactly the correct set of morphisms in the A1 homotopy category. It's already a resolution. So the naive computation is correct for this kind of groups. So this is one of the main points. And I will not explain. It's due to the list of people who work on that. It started with some theorem of Suslin on SLN. You have a lot of things to prove, and so you have Suslin and AB, and so we work on a semi-simple group on polynomial rings. But there is a lot. I mean, I cannot cite everything. Then at the beginning, I could put together the theorem of Suslin to prove the case of SLN n greater or equal to 2, to prove that this is good. Okay. Then Wendt, and with the help, there was some problem with Anastasia Stravova, completed this for the case of G of any type except SL2. Sorry, here it's more than 3. And SL2 is still correct. It was done by one of my students, Moser. So it's not for any split, semi-simple, simply connected, simple group. Okay, this is very good. It computes exactly what you want. So it behaves like a nice, so you can compute. But still you have to prove some rigidity property. Okay, and basically you may reduce using the fact that the torsors, H torsors of the defined space are trivial with the assumption I made. You can reduce basically to this case. So this is the main input. Okay, the same is true. This is the basic case to treat. Okay. Now one comment to explain on non-simply connected. So you can say something. You only have to care. Let's take the example of SON. Example SON. So it's not simply connected, so in characteristic not 2. You have the covering, universal covering, the group theory, and you have mu2 here. So a priori it's not touched by this, okay, because this group is not connected. But I just observed because if you assume you are in characteristic not 2, any Z mod 2 étal torso of the defined space trivial, then it is still true. You can deduce it. So one may deduce. So you have case by case. So basically, if the field has characteristic prime to the order of the fundamental group, yeah, things like that, you may deduce it also for this set for SON, okay, and so on. So it is just to explain the kinds. You can improve a little bit this statement case by case, and it's just what it can be done. Yeah. So some indication of the proof. I started here.
So you're using the fact that torsos of a fine space
Are trivial.
over an
Well, exactly. So yeah, if you could prove it more generally, then you could have something.
if the boundary is not algebraically closed, it's full.
Yeah, I know. Yeah. Well, but yeah, this is why I stated this. For instance, I'm not sure, so it may be wrong. It also separately closed field. But I can make it more generally. For instance, in the case of G here itself, this holds over any separately closed field. So the problem comes with taking quotient, as you mentioned. So you have to care, but there is something more general. So I don't know exactly what to put here for assumption for X to be optimal. It's okay. So indication of the proof. So I started. On the proof. So the step 1 is already over there. So first we can reduce to this case, okay, by the assumption and by this fact that due to Raghunathan, I think, that any H torso over an affine space over an algebraically closed field is trivial, is sufficient. But then it is sufficient to settle, and is this object here. So it's not only this one. It is really this one, which is very good. Behaves very good. Behaves extremely good. So still, you have to prove something. Now, step 2. So what I also mentioned, but very briefly, by the way, this assumption to be simply connected, why do I use this? The problem of quotient, but also because an algebraic group is A1 chain connected, if it is simply connected. Because in this case, the group of points is generated by a unipotent element. So anything is contractible. Okay? If it is not the case. So this is one of the reasons. Okay. So this object is zero connected, and the simplicial set is zero connected. But it is a simplicial group. So here's a trick. You consider the classifying space of this. And for the moment, I will explain. I have some other, but for the moment it's not yet finished, way to attack this. I cannot prove it without doing this. So this is a classifying space of a zero connected sheaf of simplicial group. So simplicial sheaf of groups. This one is then one connected. So, and the second step here, so it's a bit ugly, so it's quite hard, yeah? It's technical, so I will not, I will just sketch it, is to run the, so I will put a word which do not make afraid the people from algebraic topology, but basically the lower central series filtration, spectral sequence. Series spectral sequence. What is this? This is due to Ed Curtis. And it goes as follows. So I will just write this because it's quite technical. It's well known in topology. If you have a one connected CW complex or simplicial set, you can take a model for the loop space. So I took the B, so it's funny because then I took a loop on B which gives me that back. But the model is different. The model is due to Kahn, for instance. It's a simplicial group or sheaf of groups which is free in each degree. And then you can filter this free sheaf of groups term-wise by the lower central series filtration. And the iterated filtration, so the first is the derived group, so gamma, so the bracket, and then bracket of G and bracket of DG and so on. And what he proved is that this converges strongly in any, because of this assumption of being one connected. The group here, when you take the loop, is zero connected, and this spectral sequence converges strongly. So this is what I use at a very crucial point. And Mike Hopkins told me once that this is the, in fact, the main result we choose seriously this theorem once. For the moment, there is no other proof. So, because it was a nice theorem, it gives a spectral sequence, but basically you cannot use it to compute the homotopy groups. If you do it for a sphere, because the E2 term is not computable. But I don't care, I don't want to compute it. I just use it. The E2 term here is expressible in terms of a functor on the chain complex, the homology chain complex of the space. And the functor are related to the free Lie algebra functor and so on. So you have to use a big devisage and to work with carefully with the connectivity assumption, but it works, basically, because of this assumption. So after devisage using the free Lie algebra functor and its derived functors and so on, free Lie algebra functor, because the E2 term of this filtration, because the groups are free, involves this functor. So you can reduce, and you want to prove some rigidity property that, for instance, this simplicial set, after all, if I want to prove it is the same thing as the étale homology, is independent of the base field. If I extend my field to a bigger algebraic closed field, this is the same. Okay? So to do this using the spectral sequence and the devisage, I can just do it for the pieces I have. Okay? Then you reduce, and another one. So using the Breuer decomposition, cell decomposition of G, you end up with dealing with the A1 chain complex of cells. So this one. Well, you end up with the compactification of this one. So if you prefer, because this one. Because the cells in the Breuer decomposition of G are of this type. Okay, they are compactification of AN. But up to homotopy, it is suspension of, in fact, you can smash GM n times here and suspend n times. So the basic problem is reduced to this one. No, okay. The problem, yeah, that's true, but now I am leaving, to use the spectral sequence, I'm leaving the naive homology. I use the more sophisticated. And the convergence, there's a theorem which says that it converges also in the sophisticated A1 homology stuff. So I will prove the devisage using the sophisticated homology theory, not the naive one. But yeah, so I will come back to this point, the connection with these two. But it's essential point. Here, from here, it's not naive. It's really technical. I have some hope to make it a little bit more comprehensible at the end, but it's not done. So, okay. So this is the not naive. So sorry, yeah, it's clear that there is no way to, but it's worked because it is a non-naive one. So, and here you have to prove that you have transfers, and use again ideas of the type Suslin-Voevodsky. The reason why you have transfer here are quite mysterious. You have to do it by hand. You start with the free sheaf of Fabien group here. You don't have transfer in the structure. And you have to show, and this is the way I do it, that it is A1 equivalent as a sheaf of Fabien group to something which has transfer. And you just do something like the sheaf of finite correspondence to A1 with quotient in this one. So it maps a smooth variety here to the set of, well, maybe a field extension to the set of spec L in A1 over F of Z of GM smash N over L. So you have to prove that you can turn this into a sheaf, and this is an A1 equivalence. Because then this one has transfer, almost by definition, on the field, and then you have to check it respects the sub-discrete valuationary and so on. And this is the way it is done. And altogether, you prove at the end, by the last step, the rigidity property of Suslin-Voevodsky. So it is the same kind of proof that Mark mentioned. The problem, so I will come back to this point now. From the beginning, here, what is the difficulty? So I have this naive, and then I have to slowly shift to the non-naive world, because the G is miraculous. It is very good, so I can forget and can pass to the non-naive. But there is also all this stuff. Okay? It's non-abelian in some sense. When you work with cohomology theory, everything is abelian. You have long exact sequence and so on. It's much, much easier. You never, in stable homotopy theory, you will never consider this kind of functors, for instance. Yeah? These functors come into the game very naturally here, for the moment. Yeah. And this proved the fact that the homology, which of this simplicial set, so what you prove is that this is part of this one, and that this one as a space has the rigidity property. So it implies that it is a weak equivalence on any algebraically closed field extensions. But this also implies it is true in homology. So you get back your naive homology, okay, at this point. So what is the main difference in this assembled version between this proof and the proof of Suslin-Voevodsky? So a remark, and then I will 5 minutes. If I come back to, well, I will maybe use the blackboard. So remark on the situation. So if you remember, here we have the naive homology modulo L. And we have in hand this guy, or the singular A1 of X. Here we have the Suslin homology, which by the very, so this is the guy which defines this. And the guy which defines this is the motivic complex. So it is the C star, so motivic of X with C mod L coefficients. And this is the delta point with value in this free sheaf of transfer with transfer of x. Okay, this is this guy. So what makes, so the proof is complicated here, as we saw in the dévissage, because this guy is not a cohomology series, it's not a complex, it's a simplicial object. So you have to put it into pieces, which at the end will be abelian and with transfers. Okay, this is the hard part. But the rest is trivial, because the cohomology of this guy, the étale cohomology, so you work hard on this guy, but the étale cohomology, you know it from the beginning. It is the étale cohomology of x, because this one is just a collection of, it's a total space of a collection of function objects of x with value in delta n. And these are A1 homotopy equivalent to x itself. So it's constant. So the étale cohomology is just this one. You know this from the beginning. So we work on that to prove it has the rigidity property. But if it has, the homology must be this, the homology of x. Here the situation is different. You have the rigidity property on the nose because you have transfers. But you lose completely the information. What is the x group in the étale, in the category of étale sheaves from these to Z mod L? You don't know. And this is the main theorem to prove that these are the étale cohomology of x. So the difficulty is somewhere else. And this is why, in fact, they use resolution of singularity in characteristic 0. And I think the proof in finite characteristics is due to Thomas Geiser. So I saw this in one of your papers using de Jong theorem. So the proof is non-trivial to prove that the étale cohomology of this complex is the étale cohomology of x, because you lose this information at the beginning. Okay, so that's it. Let me finish with one question about this naive stuff. I will not say it's a conjecture, but what about this naive chain complex for an minus 0? So what I defined from the beginning, so you define naively a simplicial set. You can check. You can take the chain complex. Say to do this. In the case of an minus 0, for n greater or equal to 2, because it has to be A1 chain connected, which is the case for n minus 0 in that case. So what I told you, so you can check that in that case, again, like for Pn, for P1 and Pn, so we know the theorem 0, that mod L in the étale topology, it is the étale homology of n minus 0 of a sphere. And we know that in the first non-trivial homology group here, it should be, and in fact it is, known. So in, well, H star, let me put it this way. It is known that the naive, so it's non-trivial, so it's a consequence of the fact that, so this is an homogeneous variety, the SLN. So I can apply that it is also a very nice object, and so on and so on, so I can compute. So this is 0 for star smaller than n minus 1. And so this is the n minus 1 suspension of GM smash n. So the first homotopy group, or homology, comes in degree n minus 1. And in n minus 1, it is what Mark used, the Milnor-Witt K theory, in weight n here, of K for it. Okay. Now, the construction we saw at the beginning maps this to the analog of the Suslin complex, which is, in fact, the motivic complex. So it is Z, if you look at that, to n minus 1. The motivic complex of Suslin-Wojewski. Using this connectivity here, you see that the first non-trivial homology group here define a morphism of complex to this group, so Kn Milnor-Witt, considered as a group of a complex, so placed in degree n minus 1. And this is the case for any chain complex. This is the first non-trivial homology group. So there is always a map this way. And here, the miracle is that this can be put into a diagram, commutative diagram of chain complex, if you put the minor K-theory in degree n-1. Because this is known to be the first non-trivial homology sheaf of this motivic chain complex. It is a minor K-theory in weight n. So what I'm trying to say, so is it far from being a Cartesian square? That in fact maybe integrally, so this is true in the first non-trivial degree, and it is true in the étale topology. So it cannot be true in general for some reason, for Pn, so on, but for this nice sphere, and for n greater or equal to 2, I'm just asking, this guy seems to encode a lot of information, and why not dreaming that this is Cartesian square? I don't know. And this could be also a positive way to attack, for instance, the vanishing conjecture. If this were true, to prove the vanishing conjecture, so the problem is to prove that when you go up in the homological degree, this vanishes. It is a concrete problem in terms of map from delta n to an minus 0 for a big, big n. Is this simplicial set, for instance, finite dimensional? Things like that. Okay, so thank you very much.